Okay, so now let's talk about the multi-layer coding. So multi-layer coding. Now let us plot the given structure of the multi-layer coding. So this is our substrate. This is our base layer. And we have a periodical sequence of layers of different composition. Typically in most cases we have two different composition that are repeated periodically many times inside our coding in this fashion. Suppose this is the layer of one element. Above that we are going to have the layer of other element. Again we have same repetition. Okay, so this is the representation of the multi-layer coding. Okay, not so perfect. So this is the sketch of the cross section. We have a substrate. Now typically you apply a base layer made of metals. This is made of base layer is made of metals. In order to ensure good adherence to the substrate and sufficient ductility to tolerate the different strain behavior of the ceramic material and ductile substrate, and then we may apply a sequence of layers in our coating. Actually, overall thickness is comparable to a standard single layer coating, and we are still in the range of some micrometers. So how can we produce this complex coating? Typically with a sputter deposition, or we can produce this type of coating produced by sputter deposition or arc deposition method. So we have a chamber configuration represented by suppose, let me sketch. So we have an arc chamber, something like this fashion. This is the one circle, and this is the other circle here, and we have some arrangements like in this fashion: half circle, half circle, half circle, half circle, half circle, half circle, and here also half circle, and this rotates something like in this fashion. Here we have, sorry, okay, this rotates here, and this rotates in this direction, and this rotates in this direction. So we have chamber configuration represented by this sketch. So we are inside the reposition chamber under vacuum. So this green circle represents the object to be coated, and these external rectangles, means this one, are deposition sources. So if we are using sputtering process, these are the deposition targets. The half circle on the rectangle is the path of the magnetic field lines, because as we said, we exploit magnetron sources. Then we have magnetic confinement. We produce a specific path on the surface of our target where electrons are confined, and in this region we have localized erosion. So this half circle represents firstly intense magnetic field, second electron confinement, third the localized erosion. So we said that typically we have two different material composition, and for example, if we exploit the family of compounds, example nitrides, carbides, and oxides, we can produce a sequence of nitride layers. So nitrogen is a common element given by the gas phase, and different metals are provided by the targets. For example, let's say our multilayer is made up by a sequence of titanium nitride layer plus aluminum nitride layer. So in order to produce this sequence with 4 targets, means that we have titanium in this alternate rectangles and aluminum in the other 2 targets, that which are alternate and opposite. So substrate must pass in front of these sources sequentially during time. So first of all, we need an overall rotation represented by the larger circle, and that is this circle. And the objects which are green mounted on the curves will rotate in a shown way, and each substrate is exponentially exposed to all targets. So these are targets. So we produce the first titanium nitride layer. Then it moves to the second target and produce aluminum nitride layer, and so on. But we said at the beginning that we had to consider the line of sight characteristics of our process. So then in order to have uniform coating thickness, if we have complex shape, as in cutting tools, during this exposure to a single target material, we have to expose all the substrate surface possibly in the same as our target. Then a single object will rotate around its own axis in order to expose the overall surface to the target. So the rotation of this object on its own axis and rotation along the larger drum is fundamental. Now, in order to occupy chamber space in a more efficient way, instead of placing only one object on the periphery of drum, we can dispose this set of objects so we also occupy the internal volume of this chamber. So the overall cost of our process is lower. So if we put the object far from target, we can get non-uniform coating thickness. Now let's talk about the advantages of multi-layer coating over the simple layer coating. Actually, we find that this multi-layer coating are harder in comparison to this single layer coating, and also they are tougher, that is more resistant to crack propagation. The increase in hardness can be justified by higher resistance to the dislocation moment and multiplication. Actually, we know in ceramic materials the dislocation density is very low, and critical shear stress of this dislocation moment is comparatively higher in comparison to the metallic materials. But still we can produce dislocation in ceramic materials. And then we can apply the general concept we know for metallic materials. So if we create a thin layer where this distance is comparable to a layer thickness, we need a shear stress which is proportional to the reciprocal of this thickness. So a very thin single layer will impose a very high shear stress to move this dislocation inside. So the comparison, so the deformation of this overall coating is governed by the thickness of a single layer. Through the multi-component coating structure, we observe much less chance of crack propagation from the top layer to the substrate interface. Most probably the crack is stopped by these intermediate layers. So the result is low wear rate and high wear resistance. So aluminum titanium nitride or titanium nitride multilayers significantly increase the lifetime of the cutting tools used in the machining operations. Titanium aluminum nitride films, that is, they are in the ratio of 2:1. That is, aluminum to titanium ratio is around 2:1. They exhibit enhanced hardness values when annealed at high temperature, which is around 800 to 1000 degrees Celsius. Due to the formation of coherent properties of the precipitates, which are cubic titanium nitride and aluminum nitride, which provide additional obstacle for the dislocation moment. Addition of aluminum to the coating is to increase the high temperature oxidation resistance to our coating.